Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to a session on sexy types. Are we done yet? Which is a title that Simon Peyton-Jones dreamed up. And we thought it would be interesting to discuss whether where we are with research and with type systems and using types for practical programming. Have we got to a point where everything's been done? We don't really need to do much more research. How well are types serving us, or do types make much sense in a world where we've got more and more type-free or dynamic programming? So we've made a list of questions which we've asked the panelists to address. But I'm also very keen for this to be a very interactive session, so very much like to hear questions from the audience as well. So what we're going to do is I'll read out what the questions are, and then we'll go through the panelists in turn. And they've been told no PowerPoint, so they're going to give a quick verbal position statement, and then I hope we can have a kind of organic discussion. So actually, one of the questions that Connor wanted to pose was, what are types for, or are they just against? I'm sure he's going to elaborate. And another question he has is, should we infer types from programs or programs from types? So one very desirable feature of types is that they be understandable by ordinary programmers. But when you look at some of the more powerful type features in languages like Haskell, some of them are pretty sophisticated. Are we developing type systems which require a PhD in type theory to use? And if this is a mistake, should we back off and do something else? Also, are there type-free areas like, say, systems programming that could benefit from types if you did the right kind of research and innovation, or is there just no hope for types in these disciplines? And then thinking about types more widely, what's the relationship between, say, types and contracts? Do things like contracts and types necessarily have to live in different worlds, or is there some way that we can unify them? Do they live in some spectrum in which we can sensibly turn the dial? And then finally, are there any opportunities for better exploiting type information in integrated development environments like Visual Studio and Eclipse? So these were the questions that we posed. I hope that you in the audience will have extra questions as well. And what I propose to do is maybe go from right to left and ask everyone to state their position.
Well, don't tackle them all. Just sort of pick one.
I was just going to take the top question. Sexy types, are we done yet? No. Now, if you're a little dissatisfied with that answer, then you're already on the path to enlightenment as to why it's the correct answer. Because, in fact, it's only an informal social convention that the response no was an answer to that question. What's more, there was no evidence attached to the no that indicates that there's sort of any useful content or believable logic behind that answer to the question. And the direction in which types are going is to model and tackle exactly that sort of issue.
Are you I'm sort of skipping the plot here. Are you a speaker for our current coalition government?
I'll see you later.
Because I've got to say who you are. This is Conor McBride from the University of Strathclyde.
Yeah.
Scotland.
Yes. Who I am is not important.
Please, can you distribute the microphone for audience?
Okay.
Yeah, I mean, from the ground up, data is a whole bunch of bits, and interesting questions about bits are what the meaning of an individual kind of 0 or 1 choice is. Which things it make sense to do if a particular bit is 0, and which things would only make sense to do if that bit was 1. I mean, we're still in the situation where it's a sort of type-preserving transformation on programs in most programming languages, just to take every if then else and swap the then and the else branches round. And you know, if the condition is supposed to indicate, you know, somehow what is the next sensible thing to do, then somehow there's something we're not saying, you know. So I think, you know, that's the direction in which types are traveling, is to actually capture more of the semantic intent of information rather than the mere kind of machine representation of information. And it's clear once you take that as the perspective that we've got a long way to go and a lot to learn about how to do that well.
Tom, can you
So in parallel, we have the SMT workshop. How long do you think it is before we really have a widely used programming language with dependent types that's using, you know, some funky decision procedures, or, well, decision procedures?
So since you say widely used, I think it'll be quite a while. We've still got a lot to learn.
So we're talking
about the
decades.
I think we are. On the other hand, I think there will be some niches where people are really kind of keen to get a handle on their problems, where we might see some penetration earlier. And I shall try to think of 3 while I hand the microphone to someone else.
So we have, I mean, we have the contracts work, and then we have dependent types. So we also have several, I mean, we have many strains of sort of adding these, well, I see types and contracts up there.
Yeah.
So there's also that sort of split between, you know, where is that extra information put?
Yeah, I think, so one thing I would say, in terms of this question, my response is clearly the former. Since we don't know exactly where to draw the line between things like types and things like contracts, it's a real help if they're in some sort of unified framework, because that lets us feel around to find the sweet spot.
So Tom, are you really pointing out that the type checkers are just theorem provers, right? A type checker is a kind of weak theorem prover. And
So I learned it back in school.
Right.
There was
So there's a kind of
there's
blurry
some
line, right? So there's no
something or other.
So there's no place you can say, you know, this is type checking and this is theorem
No,
proving,
I
right?
understand, but
So in some sense, the answer to your question is every, you know, C# already has such a thing. But maybe that's a bit but
yeah, I know.
okay. So
It's pretty weak.
Then.
It's pretty weak
Uh-huh.
decision procedure.
Yeah. So
Compared to what they're discussing in the SMT workshop.
yeah. I'd be inclined to suggest that sort of what should at least distinguish type systems is that there's sort of some sense that that type checking is a mechanical process, whereas theorem proving is a bit more, you know, hit and hope.
That's why I was
you know,
talking about
evidence
decision
checking.
procedures, not
Yeah.
Yeah.
But so to some extent, I think you know, it's if a type system is it's always going to be a weak theorem prover, and there'll always be you know, stuff for a layer of logic on top. Because it's not, you're pretty lucky if it all cashes out from type checking. Mind you, I enjoy being that lucky sometimes.
Move on to next. I'd like to welcome Ulf Norell, who's a dependent type from Chalmers Technical University in Sweden and well known to some of his work in Agda.
I think I have my own microphone. Okay. So I'd like to talk about the first question that Connor put up, which I don't have an answer to, but I think which was the question: what are types for, or are they just against? And I think that's really a key question that we need to answer in order to push types to more people, because a common problem, and which is what you often hear from people advocating the type-free program is that the types are just getting in the way, and making that switch where the types actually work for you rather than against you, I think is a very important problem that we have to work on, and where we can actually do some good stuff.
So since you're the biggest probably proponent of Agda, and so let me ask you two questions. How old is the project? And what's the biggest piece of Agda code used by someone who is not in the Agda team is?
So those are two actually tricky questions. The project, I guess, if you go back, is about 20 years old. The current system we have now I started implementing in around 2005. So, but we've had, there's been a lot of fear improvers, programming languages coming out of Chalmers for a long time. And what are the biggest developments? I don't have any actual numbers, but there are some fairly substantial developments. Talking about lines of code, I'm not sure, but at least several thousand lines of Agda code. And
small.
That's small. Well, of course, yeah. Because it is a very young language, and we haven't really gotten to the point yet, I think, where people are actually using it for serious programming projects. So most of the stuff that people are doing are modeling using it as a math framework where you model your type system or you model some interesting thing, but you're not actually running any programs. People like to implement category theory in Agda.
Okay, so next I'd like to invite Francois Poitier from India. Do you need yes, thank you.
Hi. Yeah, so I'm not sure which of these questions to address, but actually one question which I'm thinking about at the moment is, what are types for? Are they any use at all? And the question the reason why I'm asking this is that yesterday, for instance, we saw people program things like real-time operating systems or flash file systems in C, and then they go off and they prove that their code is correct using theorem provers, and they completely skip the type checking step in a way. There are no fancy types in their code, and yet their code, if they go all the way to the proof, their code is going to be 100% correct. So the question is, what are types for? Are they still useful? And I imagine there is a way for them to be still useful, perhaps by making partial correctness proofs easier. So I'm trying to understand how types could be a useful and cheap first step towards proofs of programs, but I'm not completely sure as to what the best way of doing this is.
Thank you very much. Perhaps we can have a position statement from Santi Jones from Microsoft Research Cambridge.
What are types for? So I liked your question too. I think in some ways we undersell types because we present them mostly as a way to be against things, to reject bad programs. But types are the world's most widely used formal method by far, and mechanically check every time you compile your program. I think that's a great thing that we could build on, right? And so one thing I really think that therefore is design time. I used to be asked, so in functional programming, what do you do instead of UML? And for a long time I thought that was kind of an embarrassing question. Well, you know, OO guys had this wonderful UML stuff that helped them build, you know, design their programs, and then they went and built them. And then I realized that actually types are our UML. That's what you do when you start designing a program, is write type declarations. Rather ironically, Matthias Verleisen's book, How to Design Programs, which is a lovely book. The you know, phase, I don't know, or 2 of the program design phase is write down the types. That's part of how he thinks about design, even though Scheme is an untyped language. So design and maintenance, that's the other undersold, unsung aspect of types, is that they can, when you've got a big program and you want to change it, you're brave enough to change it. If GHC was written in C, even if I proved it correct, I would never dare change it. Right? As it is, I change it every day in a suite. So this is a big deal. A question I want to ask all of you guys is this: as type systems become more elaborate, in an ideal world, you have some kind of specification of what it means for a program to be well typed according to your type system. And that's something that you are meant to explain to programmers independent of any particular implementation. And then the implementers are meant to go off and implement a compiler that will accept every program that meets that specification according to the type system and reject every program that it doesn't. But as type systems become more complicated, the specification itself of the type system becomes really quite difficult, and perhaps not something that individual programmers are going to understand. So I kind of wonder whether you get to the danger is you get to the point where a type system is more or less defined by its compiler. So in GHC's case, we're already at the stage I don't have a formal spec for everything that GHC does. And I kind of wonder, and it's certainly true for C# and F#, I believe, that the compiler makes some best efforts to type check things, but small changes in the program can cause, that you might think would be innocuous, can cause the program to be rejected, and that those changes are they're nowhere specified. So the question for all of you is, does that matter? Or is it maybe it's okay at the edges, for the fuzzy edges of type systems be defined by compilers? I don't know, but I just noticed that in practice, as we get more ambitious, that's happening more and more rather than less and less. You know, in the days of ML, we could say, this is, you know, these 5 rules define the type system, and nowadays that's not really true anymore.
Finally,
question for you, Lord. Right?
Yeah, and finally, I'd like to introduce Eric Meyer from Microsoft in Redmond.
Yeah, so Simon, I need to correct you. In C#, we actually try to make the type checker really predictable, because it's really and so you limit the expressiveness of the type system to make it more predictable, such that, like, you know, for example, in Haskell, where you get kind of crazy error messages, you don't get it. Or in F#, you know, there is like, you know, sometimes you change the order of your program and it doesn't type check. So in C#, we try to prevent that by making the type system weaker, because it has to be always predictable.
You should talk to Gavin.
Okay. Now the other thing is, I think types, except for in Haskell, are pretty useless, because, you know, if you have a Java or C# program that says that it's something from end to end, there's nothing you can infer from that type, because the types only capture a very small part of the behavior of your program. So in some sense, they're more, you know, it's like gives you a false sense of security. And I think the only choice, reasonable choice that you have, is to make your language pure and have all the effects visible in the types. But then you get a type system like Haskell, where, you know, I have to admit, it is way above my head. It's too complicated. For practical people, I think we are a little bit in a difficult position. Another thing, as you say, if the type systems become more sophisticated, we forget the social aspect or the human aspect, because people make mistakes in types and in programs, and when you have mistakes in your program, there's debuggers, and most real developers, I don't know, the developers I work with day in, day out, they get an existing program that's like millions of lines of code, and there's some bug, and now you go figure out, you know, where's the bug and how to fix it. If types get more and more complicated, we have to debug. Maybe I made a kind of mistake in my types, and now I have to debug them too. And I think we don't have the tools to, if you shift that work from runtime to type checking, we need to have the same kind of support and tooling to do type debugging, and not just saying, this thing doesn't unify with this thing. Error. Yes. And so I do believe that there's a lot of human engineering that, you can have the most beautiful type system, but if you don't tackle the aspect that it's humans that have to interact with that and have to struggle with it, it will never succeed.
Can I ask if there are people?
Can you say something about the effect of dynamic in C# on the type system?
Sure. So in C# and before that, actually in Visual Basic, we allow a combination of dynamic and static typing. And the strange thing is that, again, when I said, the type system doesn't really give you any guarantees, is that all you could do everything that C# dynamic allows you to do already using reflection. So if your runtime supports reflection, now you can go off and at runtime do everything dynamically. And the type checking is really weak. And people have tried to come up with type systems that when the static types are okay, then you know that at runtime nothing goes wrong, but those are even more complicated. So what dynamic in C# really is a way where you do reflection-based programming in an easier way. So when you write dynamic, you say two things. You first tell the compiler, shut up, I know what I'm doing, and it will put in all the boilerplate code for you to do reflection, the reflection-based access. And in practice, that works quite well, but it's also a little bit weird. For example, in .NET, and Don Simon, is he still here? Yes. So in generics in .NET are not covariant, only for interfaces and when they're safe. But for programmers, like arrays are covariant. So an array of person, I can pass that where I expect an array of object. And the real, type theorists say, oh, Eric, that's bad because it's unsafe. But in practice, that's great. You just do a runtime check. Now, with dynamic, I can still get covariance, but now I have to throw away all my types. I have to make my list of person into dynamic. Now I can manipulate it, and then I have to cast it back. So in some sense, there was already a loophole, but you're now, by not accepting this kind of, a little bit of type unsafety, you're forcing me to kind of, go and forget all the types. So I think we have to be really pragmatic, and dynamic is one step, but we have to be very pragmatic and say, covariance, yes, that's unsafe, but the whole language is unsafe. So why, don't allow this little unsafeness where the rest of the language is completely unsafe? And I think Haskell is really the only language that takes the fundamentalist approach, which I really admire. But
what a dangerous compliment.
But you see, probably the whole world's Haskell population fits in this room. So, that's also not good.
That's a good thing too.
Maybe, yes.
Some of us are even more fundamentalist.
Yes.
Actually, just to follow up on that point, I wonder if there is any data at this stage whether, how much dynamic is being used. So anecdotally, one of the interns that, not of mine, but I should point out, but of somebody else's, that sort of shared an office, I would sometimes look over his shoulder, and his code was just full of dynamic types, and they were just kind of spreading all over. And as his internship progressed, I think basically the percentage of non-dynamic type became fairly small. So what are your thoughts on that, and what do we see in the field, if anything?
Okay, so that's a good question. So, and it's kind of obvious how this behavior starts. For example, if you look at the way most web services are defined today, if you go to Twitter, in the olden days, people would have when we were still using SOAP and XML schema, there would be all the web servers would be strongly typed. But right now, say you go to Twitter, you get back some JSON, and the contract is specified in English. It says, there's an examples, like, if you make this query, you get back something that may have these fields. So there is not even a type that describes the values that you get back. So in many cases, when people interact with web services or other parts of the system where there's either a different type system or the types are not well specified, they start to use dynamic. And once you start to use dynamic, then you're going downhill or uphill. It's yes, because imagine that I get a list of things that I don't, whose structure I don't know. Now you have, you can say it's list of dynamic, but now when I access the elements, I get back something of type dynamic. And so from there on, once you have something that has dynamic type, you don't know anything about the types anymore. So whenever you access it, it remains dynamic. So it's quite viral. It's a little bit like the I/O monad in Haskell. So once you're in the I/O monad, it's the proof obligation to say that this is not dynamic is quite hard.
Is there also a tendency amongst inexperienced programmers to say, I got a type error, so I made it dynamic?
That's trying to combine
and again, that is also, when I spoke about the social aspect, the human aspect, people enjoy more to debug their programs at runtime. It's easier to find a type error using the debugger than to find the type error in the compiler.
Oh, you made two statements. One is that they enjoy it more, and the other is that it's easier. I think I agree with the former. But I would question the latter.
Really?
Oh, what do you think?
Yes.
Well, it depends how well you understand the type system. I mean, you were saying earlier on, is it important that the type system should be predictable around the edges? And I still remember my experience coming in as a C++ programmer and trying to learn ML, and it was a total nightmare, absolutely total nightmare. So one of the questions up there was should you infer types from programs? And I gave a talk once about entitled "Why I Hate ML" in the LSDS. So part of which was type inference considered harmful, because you're sitting there as a programmer and you don't understand the type rules, and you don't understand the error message, and sometimes you know that bit's got to be correct because the compiler didn't complain about it, but you don't know what time it is.
Yeah, if you've got questions, you can raise your hand so I can give you the mic.
I've forgotten what the question was.
But there's a man in front who's got a question.
The question was to do with was to do with debugging, so that the programmers might enjoy debugging runtime errors more, but will they find the error more quickly if they're looking at the entrails of a bunch of heap objects than if they look at a type error that points them straight to the source? I'm not prejudging the question at all.
How will they understand the type system? Does that type error make sense to you?
Andy had his hand up for a question.
I wanted to come back to the Twitter example about how the web seems to be getting less well typed. I mean, XML schema was a dreadful type system, and it was sort of a conspiracy, I think, by some of the big corporations to try and lock people into their development tools and hence their platforms. And so I think SOAP and XML schema kind of went away in favor of stuff like JSON, which is like not really typed at all. So what do you think? Is that inevitable, or could we see nicer type systems for the web? Once we've recovered from the mess of XML schema?
So to be honest, if you look at XML schema, it's like people like Phil Wattler that tried to kind of inject some dose of research in there and made it into a mess. Not so much of the big corporations, but so I think.
This is being recorded.
But what I'm not trying to pick on Phil per se, but I think but I do believe that the academics, that I do blame the academics that they let this thing kind of slip, and then they came in, and trying to make it into something complicated. You see that now with JavaScript too. So JavaScript, is somewhat of a mess. It grows organically, and now we have to be really careful that, you know, and I think it's a good idea that academics are now entering the JavaScript committee, but we should be careful that we then don't, you know, create an academic type system or an academic language that makes things in some sense worse and complicated. Now the other thing I think for the web in particular, there it's extremely heterogeneous, and so data comes from all sources and so on, and I don't believe there exists a universal type system, because the type system can never keep up with all the different forms of data. Or for example, you know, do we have a good type system to describe graphs? You know, if you think about RDF or something like that. So I think it's just too hard to come up with one type system that covers everything. And then it's probably better to have no type system and then just type at the edges. When it comes into your system, you have your type system, you check the data, and then when it goes out, you somehow publish it. But it becomes, again, more like a social contract. I don't think there is a universal type system that will work, because, you know, you will get something like XSD, which is an interesting example. I don't know if people remember XML, but XML, the structure of XML documents is very unlike the structure of trees and so on, because there's mixed content and so on. So, and now you're trying to type that, so you're trying to combine grammars with types and functions, and inevitably that will be a mess. So don't even try. Oh, and now the port.
Maybe, yeah.
I don't have anything to add.
There are a couple of things I disagree with you, but I think you expected people to disagree. When you say that types, we don't want to debug them statically, this seems like a contradiction. If we don't believe in that, we don't believe in types anymore. And actually, I'm surprised, because we were supposed to talk about sexy types, and now we're talking about no types, no more types, or just textual types. So, of course, an example of when you like types very much, if you have in ML, it's not just Haskell that has normal types. So in ML, if you do data type definitions and then you add a new case, then you're so happy, because the type checker will point you to all the locations in the program when you need to change your code. So this is, I think, a very nice example of where types actually are a debugger, rather than you need a debugger to correct the types. Well, I think that's all for now.
So I think Didier makes a really good point there. I think that also speaks to the question at the bottom. You know, that there are so many opportunities we're not yet taking to let types play a much more active role in the program construction process. It's very interesting to watch the interactive experience of typeful programming in a system like Agda, but that supports a tiny fraction of the development cycle, you know, where you think you know what types things ought to be and how to write your program, and you start working by refinement towards a completed program. And then the moment you realize that you got it wrong and that you need to go back and change your design, that's the point at which the technology stops helping you. And you know, we need to support, you know, the other 95% of the development process, where we're going back round the redesign cycle, tweaking something and trying to find all the places where we need to do something slightly different, where we need to add an extra argument to a function, where where an extra case happens in a pattern match, all of that sort of stuff. We need to be you know, exploiting type information to support that. There's just so much room to do that, and well, yeah, if we haven't even got error messages right yet, you know, when are people going to get around to doing that?
So let me address the question that I think Simon posed, and I'll actually agree with Eric on this one, which is that I am actually all in favor of doing things at runtime and debugging. And if you by way of report from the trenches, if you will, if you watch very experienced developers, what they often do is they use Visual Studio's, edit and continue all the time, which is to say they're editing their program as they see values at runtime. The problem is that the same logic applies to fixing effectively type errors or what could be expressed as a type error by observing real values at runtime. The problem then is that it's difficult to connect your understanding of what went wrong with a fix that would be done statically. I think that's where work is needed.
I don't know how you're going to say this. So I just can't imagine that you if you have somebody who's produced a value that's the wrong shape for its consumer, but this value that was produced has been stuck in some data structure and passed around, and it's been through some immense amount of plumbing, and then finally it pops out at the end, and somebody says, "Oh, I didn't expect to see that." Then it's very far away from the producer, and finding a way back to it. Whereas type system just nails it right there. It says immediately. This is never going to work. It just can't work.
So Simon, this is, and I think that where you see the real problem with type systems is that you can only specify parts of your invariant. So even if I'm saying this is a list, there are a lot of other things that I kind of assume or expect. So out of the end comes a list. Yes, the type checker has allowed that, but it's still not what I expect. So you still need to do runtime debugging. So if the type system only helps me with half of my job, then I might as well just throw it out of the window and do all of my job with a debugger.
So it's like saying that, because the roof of your house occasionally lets a little drip through, you might as well not have a roof at all.
Yes, and then you can enjoy the sunshine.
It's time for the audience.
I think the other danger is that you can develop the following methodology. First, write a typeless program, and we know that in Lisp you can manipulate lists that couldn't be typed, and then after it runs, and then you say, okay, now I have more time, I need to maintain. Now let me introduce types, and that can be very dangerous, because maybe you won't be able to.
Yes, although, and I think, but that's maybe what you were saying too, right? Is like I think. The process, when you are writing code, you don't always know yet, what you want to do and what your invariants are. So there's always, even when you're writing types, and especially I think if you have dependent types and so on, you're always refining your types by making them stronger. So I think if you have a very expressive type system, you can do that. But in Haskell, you cannot. I cannot say, I expect my list to have prime numbers in the even positions and odd numbers in the odd positions.
Not yet.
Oh, not yet. Okay. Okay.
That's right. Ulf could do this.
Yeah, no, but it's a very valid point, and it goes back to what Connor was saying. That in Agda we have this very nice interaction when you're doing the right thing, but a very important thing is because you don't always do the right thing, and in fact very frequently you do the wrong thing. So getting to the point where we have also support this, you started with lists, and then you find out that actually I need those prime numbers to be in the even positions. How do you take your program working with lists, add that extra position to the type, and then just have the type checker tell you about, oh, you need to insert some extra stuff in here to show that, or here you're inserting a non-prime number into an even position. You have to fix that.
So I have a question for you with that respect. So one of the things that when you're building libraries, is that you want your libraries to be reusable. So for example, you want a library that has like hash tables and lists and so on. But once you add more and more stronger invariants, the reusability of your type gets less and less. So how do you deal with that?
I think Connor has something to say on this.
I think I will plug my new paper at this point. It's called Ornamental Algebras, Algebraic Ornaments, and it introduces this notion of an ornament, a way to take a plain type and make it fancy. So instead of just saying, I've had a brilliant new idea for a type, it came from nowhere, goodness me, look at the programs I can write with it, you say, this type is made from that type by adding more information, and then correspondingly you get for free the ability to throw the extra information away and communicate the refined values back to the library. You can also, if you've explained that the extra information is added in a systematic way, you get the conversion both ways and some round-tripping results. And then you can also start to ask the question, and this bit is in the future research for the paper, if we have refined our type in this way, how much extra information do we need to lift a program on the plain type to a program on the fancy type? So these things then just go in smaller increments if we have the presence of mind to point out the provenance of the type.
Yeah, it's really two comments, but it's still the debate between Curry and Church which is raging on. I mean, you in the role of Alonso Church and Eric with Haskell Curry. What's difficult to explain to students, and there I will second Perdita, so they start with like scheme, and then we show them how to code a fixed point, and they're really happy about that. Then we want to write it in ML, and you can't, because there would be a type error. But then the student goes and says, yeah, but there is no runtime type error in scheme when you run your fixed point on at a fixed type. So there is a step somewhere that has to be explained to the student. This was just two comments.
I also wanted to comment in answer to Eric. So you said basically types are descriptions of data, and we could just as well look at the data at runtime using a debugger. But more and more types are more than just descriptions of data. We also have types to reason about ownership at the moment when you have mutable state, and also types to reason about the permission to interfere with other threads. And those are perhaps much more useful than just descriptions of data, because it's very difficult to debug when you forget to deallocate something, or you keep the permission to some bit of memory even though you should release it and give it to someone else, or debug concurrent programs. That's very difficult. So perhaps these are the areas where types could be even more useful.
Yes. So I agree with you, and this is what I tried to say in the beginning, that currently your types don't say much about the effects of your program. And what you're saying is that if the types are more expressive in terms of the effects, like these threads are reachable, or this part of memory, then it becomes useful. But the current type systems for most, like Java and C#, I do believe that they don't really add a lot of value, because you cannot, if you give me the type, like there's no terms for free, and if there's no terms for free, then it's worthless, I would say.
So following up on this arranged, or how you called it, types.
Ornaments.
Yeah. So I think it's probably overly pessimistic, but I bet this idea, so I like it very much, but it would never make it into some prototype branch of OCaml. Yeah. And my question is why you wouldn't even try to do it? It'll never go beyond the paper, even if you like it so much. My question is, it's a bit provocative, but why don't you just do it? Pardon?
Why will it not go beyond the paper? Why will it not go beyond the paper?
That's the experience. So if you look at the changelog of OCaml, so recently, so there were just 3.12, there were some minor changes. But so nothing happens for the sort of in this kind of direction. And so why don't you just go take this interesting ideas and put them to work and let people play with them and appreciate them? Use them.
I guess you can't blame Conor for OCaml's lack of evolution.
well, you can perhaps observe that the people who get excited about sexy types have gone somewhere else. I mean, that's with some notable exceptions sitting in the room, of course. But I think that's often the case. Yeah, I mean, there's clearly a long way to go before any of this is more than sport for people with PhDs. But that said, don't take it away. I mean, I don't want to go back to the place where the types don't express the things that I mean. It's now a question of personal liberty as far as I'm concerned. I will not be deprived.
But that's exactly what I don't understand. You have this great idea, why don't you just go full way, put it into compiler and make it work? So it never goes beyond the paper for anything like OCaml, SML, so languages that significant number of people actually use.
If you look at Haskell, I think that's not at all true. I mean, Simon, I'm sure you have.
No, but so let's not move to Haskell. Let's.
If your so if your question is why does my stuff never get beyond the paper, that is not a question for me, but for British funding agencies and my employer.
Yeah, so I'd like to disagree with the comment that Francois made a couple of minutes ago. So I think it's purely an accident that the current execution machineries just carry the type information around. So right now in the debugger you can only observe type clashes, but I mean right now we see contract systems coming up which check all kinds of things dynamically, and I've seen, I mean, there are dynamic semantics for ownership systems, so why can't you encode these properties dynamically as well? I don't see a real showstopper there.
Yeah, I guess maybe you could. Yeah, there would be some overhead. I guess,
sure.
Like runtime race detection, some people do that.
Yes,
but I don't think it's very easy to do.
Andy, you asked a question.
Yes, I was wondering about. Well, I mean, coming back to Andrew's question, I think I think he's asking about the difference in spirit between sort of the verification community and say the dependent type community. I mean, like on the one hand, there's an obsession not to change the code and somehow get some automatic provers to prove correctness, like the SLAM work that Tom did and. The work on OCaml that you guys are doing, I guess we're trying to do that too in the refinement types work with F7. We don't want to change the language, but because it's out there and there's compilers. On the other hand, the dependent types community, I mean, some would say are obsessed with foundations and care rather less about whether there's much of a code base that they can apply their techniques to. I think that's what I was thinking when Andre said that. There's this kind of chasm. It's almost like two parallel worlds. So I mean, can these, and so supposing there are these two parallel worlds, fair enough, different objectives, longer term, shorter term. What does the panel think? I mean, can these two communities, the fundamentalists about current code versus the fundamentalists about foundations and future languages, what can these communities learn from each other?
Well, I certainly think it's important not to be exclusively in one camp or the other, which is one reason why I've started my terrorist campaign to smuggle as much scary typing into Haskell as possible, preferably by the front door. But at the same time, we're obsessed with foundations, partly because we were aware of a number of significant foundational problems that we've got to get right before we can do anything realistic. I mean, so the thing I would think of in particular in that respect is co-induction and reasoning about co-recursive processes that's currently in all major implementations of type theory a disaster. If we're going to talk about real systems, we've got to actually have something sensible to say about that. So, I think there's, there are plenty of foundational things to think about. I mean, we should certainly not give up on that, just to get real sooner rather than later. I think there's certainly room for both, and there's room for communication across that gap in both directions where possible. That's why I try to work both sides of it.
Simon? So I think there's maybe hidden in your question something really also like about the church versus Guri view of types. It's like, should a program, have meaning when it has no types, or should it only have meaning when it has types? And I strongly believe that you should define the meaning of your program independently of whatever type system, and then you layer your type system on top, and just, it should always be executable. The type system should be something optional that can evolve by itself, but it should never determine the execution and the semantics of my code. And I think in the extreme it means that also that now your values at runtime must contain some type information, because you cannot erase that, which is something that the other camp tries to do for reasons of efficiency, but then you throw away the ability to run the program without knowing anything about the types.
I profoundly disagree.
That's why you're on the left side and I'm on the right side.
No, so
you make an assertion. You didn't say why you think what you think.
Okay, I can. Well, yes.
Made a claim.
Yes.
So you have some evidence, adduce.
First of all, I think that your type system can never, or it's really hard to make your type system expressive enough. We had the example with a fixed point combinator. Now you have to then write recursive types, or there's certain things where the type system is not powerful enough to express the behavior. On the other hand, I am a programmer myself, and I don't trust that the type checker is correct. So if I'm kind of, erasing all the types, assuming that the type checker has, now it's safe, then, I would rather have a lock on my door, that is checked at runtime, whether it's really locked, instead of erasing all the type information and just assuming that the type checker was right.
So you're going to, can we have a promise in writing that you're going to give up using ad hoc polymorphism?
Well, I'm laughing because that, if you look at the C# and the VB specs, and my guess is F# as well, that is the most complicated thing of the whole spec. It's static overload resolution, and that makes the language really, really complicated. On the other hand, it's like crack. It's really, really convenient, because one of the hardest things in programming is coming up with names, and with ad hoc overloading, then I can use the same name, and I can be lazy, and so there's a tension there.
And in even more kind of higher order situation, think about using monads in Haskell. There's an awful lot of plumbing code that you just don't write down, because you've got a type that is explaining what the plumbing has to be for that class of problem. So what's really going on is that types are not just describing data. Types are describing the essential structure that's in play when you're manipulating the data. And the point, the church agenda in the long run is, by keeping the types written in the program, is to start rubbing bits of the program out. Right? You're clearly on a win when it's a question of, shall we write the program with type annotations or without? But if keeping the types in lets us rub bits of the program out, if types are a kind of high-level design statement and the program is just bridging the gap between that design statement and something executable, then we're actually much closer to programming at a very high semantic level than we were before.
Let's move on to another question.
So it's a question for François. Could you come back to your initial point about people developing program in a typeless way and then afterwards having it model checked and so on?
Yeah, I'm not sure what to add, but well, as Simon said, I guess this is something you can perhaps do easily once if you have a big piece of frozen code, and then you can go to the effort of proving it correct, and you don't need any types if you do that. But if you want to maintain that code or to restructure it, then I guess, as Didier pointed out, then the types can be very helpful. Did you have a more specific question?
Just in the light of the discussion.
Mm-hmm.
Yeah. You know, if you do that, very few people do that, right?
Do what? Sorry.
Do the even if the code is frozen, very few people do the formal verification stuff.
Mm-hmm. Yeah, more and more these
really
days, but
tiny.
still very few.
Well, there's a lot of people use types. I think I don't think that technology is, and I think it's useful for kind of specialized high high assurance situations. I just can't see it being the thing that everybody does routinely, every programmer, every day.
Not yet, I guess.
Not foreseeably.
Can I ask enough to my friends here, the kind of the typeholics, like if you look at
you're a common typeholic. After years of rehab in Redmond.
But if you talk about high assurance systems, if you look at a language like Erlang that's used for building distributed systems and so on, that is not strongly typed. But people, again, there's like certain patterns, design patterns that people use to make their systems highly available. And I think it would be quite hard to express those in the type system. So, I think maybe Erlang is maybe the prime example of a language that is used to build highly available systems that has no type system and still very successful. So. Maybe that should make you think, Simon.
Oh, it does. So I'm imitation is the sincerest form of flattery. I'm busy trying to implement Erlang in Haskell, literally by reproducing its failure model. But the Erlang's idea is, if anything goes wrong, shoot down the process and recover. Right? And they have a very clear notion that you can shoot down a little bit of the program, and shooting down that bit isn't going to affect the other guys because they're in completely disjoint memory spaces. But you can do all of that in a strongly typed language. In other words, it's the roof argument again. You just need sort of defense in depth. Why give up the roof if you initially you also want a machine gun nest? You should have both, right? That's good.
But for example, like if you look at a function, say I'm in a strict language and I have a function from int to int. Now people say, oh, I always know that what I get is an integer, but if the machine goes down, now I don't get an integer. So even those failures are not expressed in the type system, and Erlang deals with them. So how would you express in your type system that the machine can go down, or your memory might be corrupt, or something like that that are external factors, and that are very operational. From a machine point of view.
I have a mic, so perhaps I can answer. I'm here. I don't see even if you're not in Erlang, you have things like Stack Overflow, which is some outside factor, and we use exception for that. So I think the same kind of thing could be done if you type. You could have exceptions are kind of dynamic, which you so you raise them, and they may raise at whatever you don't raise them. So I think there is a path there in Erlang. You said that Erlang, this wasn't the question I wanted to ask, but discussion switched to Erlang. You said that Erlang is very successful. Yeah, sure, and it's not strongly typed, but I sustain Simon. I think it could benefit a lot if it were more typed. So the question I want actually was more a remark between the position you were taking that programs should be, the semantics should be untyped, and Connor's point of view, which is the other way. I think I'm a little bit, I'm more on your side. But I take Connor's, so I like the runtime to be untyped because I want to erase type, because I want to be efficient. And if you need, when we define the semantics of program with types, we compute over types. And if we have to run the program with all the types, it's amazingly expensive. So we want to avoid that. However, I also, like Connor said, there are things that at some point, so far in ML, it's mostly, the runtime is mostly untyped. There are a few tags, but if we want to do more structural programming, more class type programming, which we don't have in Camel, but we would like to do if we found another interesting way to do it, then we'll need something in between when the types will influence the semantics. The way I like to see it is that there should be a language in between, that the semantics could be, you could erase all the types, because there would be enough explicit information, dynamic, like coercions or tags. So I would not call them types, I would call them tags, that are going to drive a semantic, and this would be enough. So if you're in a surface language, the types will drive the semantics and the compilation to this intermediate language, where now you just have a very weak notion of types that I call tags, and now you can erase them, so you don't have to carry the times all the way through.
I completely agree.
Do you completely agree too?
Surely not. No. Sometimes I am also in favor of the golden middle. And in this case, I think if you could achieve that, that would be great. But I think that's still an open research problem. And being, you know, somebody from a product team, I cannot take a dependency on an open research problem. So I'm not saying that I don't like your idea. If that's available, I would definitely use it. But at this point in time, I think for me, the only reasonable choice is to carry around the full type information at runtime. And I would be happy to kind of, you know, throw some of that away if your research has, you know, become mature enough that we can do that. So yes, I would like, you know, I think this is a good path.
But there is a paradox in what you're saying. You're saying you'd like the types not to influence the semantics, and at the same time you'd like to keep the types at runtime. So what's the point of keeping them if they don't influence the semantics?
Okay, I'm a man of contradictions. The reason you want to carry around the like, for example, even in object-oriented language, when you're doing dynamic dispatch, you know, the V table is a representation of the dynamic type. But also, if you want to do reflection and things like that, there, you know, you need to be able to inspect the types at runtime in order to operate over them.
Okay,
but
so
what I mean is that I don't want like where the program has to be well typed in order to run. That's what I mean, that I don't want the types to influence the runtime behavior. It should be, you know, the meaning of your program should be defined independent of the static type. It can be defined in terms of the runtime type,
okay,
but not in terms of the static type only.
I have a question regarding type inference. Should we strive to have, you know, the Javas and the C# of the world, or the future, whatever, have a type system which is more amenable to type inference a la ML or Haskell?
That's a very good question. So, for example, when we designed the C# and VB type systems, we did not use unification, for example, to do type inference, because with unification, the place where, you know, the type error really happens and the place where you know, find it can be arbitrarily far apart, because the unification is bidirectional and so on. So we had a much more limited form of type inference to make it more predictable. And so I think most developers like type inference, but it must be extremely predictable. It should not be some magic. And I think you should always be able to pinpoint exactly the point where the type error happened, if there's a problem with type inference. And that restricts, you know, the kind of type inference that you can do.
Yeah, but you also want parametric types still.
Yes. Yes. Although, again, they are not parametric types in the sense of, you know, parametricity, right? They are more like passing type parameters around. Yeah.
So, Eric, in your view of the world, it seems like you want the benefits. You want all the benefits of type systems, sort of at not just at compile time, but at runtime. And at runtime, you can do like marvelous things, right? Because you have all the state. So you can do very deep checks. And you know, how can you envision an infrastructure that really supports that? I mean, just to give you an example, lately I just started digging into WPF. Oh my gosh, routing events and bubbling, and the thing goes up and the thing goes down. And you know, we had something that was called attribute grammars, right? And it's all embedded in there, and it's totally dynamic and plumbing. And you know, the thing type checks, I mean, and the compiler passes, and then nothing happens, and I don't get any runtime stuff. So how can, so the problem is, you know, I mean, it's XAML, it's great, the compiler tells me some shit, and then there's this incredible parameterized dynamic behavior, but the runtime checking is just non-existent. I mean, it just swallows some things, and nothing happens, and then I go, and you know, basically my, as you know, the sort of type checker or type inference tool is Bing or Google. It's like, okay, I have these words, bubble and things and user control, and I put them into this great inference engine. And usually what's amazing to me is I get some sample code that comes back and somebody says, oh yeah, drag and drop in WPF when you're doing user control with the bubbling, blah, 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 blah. It's like, it's amazing, right? We're just running, I mean, the industry is running so far ahead, but we don't even get good runtime checking. So what's the hope for even typeset runtime? You know, because even in WPF which has rich stuff, the experience still sucks major league when you're trying to do anything beyond sort of the simple stuff, the really simple stuff.
Okay, so I can answer this, but I have to say here that this is my personal opinion. I think
everything else has been
no, but here, yes.
That was not a Microsoft.
Yeah, exactly. but since you kind of now, since you're talking about a specific product. I think WPF for me, and the example that you show, well, but I think I think it shows the weakness of domain-specific languages. I'm not at all a fan of domain-specific languages. I think the road to hell is paved with domain-specific languages. Yeah. But since XAML is a programming language by itself, and it's a domain-specific language, now you really have to do the same things if you want to implement it correctly as if you would implement a regular language.
XAML is independent of WPF, right? I mean, XAML is just this framework for reifying the objects in the .NET type system into XML and making that go back and forth, right? XAML is, I'm complaining about WPF.
Yeah. But the XAML, that is the language in which you express a lot of your event handling and so on, and that is the syntax, and then there's the runtime behavior, which is the runtime semantics. And what I think is that we should not do domain-specific languages. Let's just do, express everything in a programming language, and then, the people that implement the programming language have the requirements to make this all work at runtime. And we should not do domain-specific languages.
Can I just a question
are you
regarding?
Going to keep on this topic? Are you staying on this topic?
Yeah.
Okay.
It's just a small question on domain-specific languages. What's the difference between a library in like functional language and domain-specific language? Because it seems to me that the two things are very often the same thing.
Yes, but now, of course, there's a spectrum. But if you look at XAML in particular, there are things that you express in the markup that you cannot express in code. For example, dependency properties, routed events, all those semantic concepts are things that you can express syntactically in XAML that are interpreted by the WPF runtime, but they don't have a correspondence in C#. C# doesn't have, and .NET doesn't have routed events and so on. So, and there I think you now see you have a domain-specific language that is really a quite powerful language. It's just not like a little language. And now there's a mismatch with the semantics of the real runtime and the runtimes don't have the same quality in terms of debuggability, etc. So I think, for me, the root cause is the fact that, somebody went off and designed their own language with syntax in XML and some runtime. And I'm very conservative. Designing languages is really hard, so let's have a few people do that really well, implement that really well, and then build on top using libraries. And if you want to call that a domain-specific language, that's okay. Embedded, yes. But not an external domain-specific language with its own runtime.
Can I rephrase Tom's question, going back to the place that you started, Tom? It sounds as if you're saying, well, if you use this complicated program, then some error happens, but the error doesn't happen in the form of some piece of code expected an integer and a runtime type check found that it was a character, and so you've got something concrete to get your teeth into. Instead, it's an error. The form is the wrong thing happened. It was just silent. No window appeared, right, or something like that. Am I kind of in the?
What I'm saying is that the runtime type checking can be incredibly powerful, right? If I want
But what if it doesn't happen? Is that so the program goes wrong, but it doesn't go wrong in the form of a runtime type check error, right? That was your problem with WPF.
Well, I since the compiler said okay, and then there's this very complicated runtime semantics, it would be nice to have better runtime debugging or better dynamic invariants, better contracts that are checked there that help guide me. Because we know there will be some things that I can do statically and some things that I can do dynamically, and maybe we need to have a better structure for creating better dynamic runtime checking, and when people think about their languages, really think carefully about that division. And clearly over the last couple of days, I would have been maybe a little bit more productive. I don't know. It's hard to say. Like, where do you divide your time in terms of your resources? Do you let if you make really complicated things that people use a lot, then you get a whole consultancy business, and then they'll publish stuff on the web, and you can go search for samples and things like that too. So, I think there's lots of information about program behavior out there, and I was just saying that, I wish at times that, I'd had better runtime checking, and if that was a runtime type with better checking, that's acceptable to me if the thing can't be statically checked, right? But what's unacceptable is sort of like, this very mysterious system that I sort of poke, and it's a black box, right? And I just observe, this whatever behavior the designer just said, well, that's all you should know about. But then they do all this stuff for me, or behind my back they do weird things, like they capture some events and they don't capture other events, and I don't really know, and the discovery becomes difficult.
Maybe I should just say where I was trying to go with my question, which is that you're a person who puts assertions in his code a lot, right? Because assertions are like extra runtime type checks. They say things that I expect to be true, and I kind of expect the same thing to be true. This goes back to type systems just against things. You often, if I'm right, I might write a more restrictive type because that's what I expect to happen. If it doesn't happen, the program would still run, right? But something weird is going on, and I'd like to know. So just for the same reason I put dynamic runtime assertions, I might put static assertions, and that's often the way I think of type systems, is they're expressing my expectations about the way things are. And if it isn't like that, then I'm into la-la land because I'm programming against something that I really wasn't thinking about when I wrote the code. So that's now things are dangerous.
So essentially what you're asking for is that every domain-specific language should have a printf statement.
No, I want the abstractions to explain why they fail.
Yes.
Right? When I link them up in certain ways, and it can't. No, I don't. It's got to be a lot better than a printf statement. Right? It has to explain to me what went wrong, right? Which is much more difficult.
It would be as if in Java or C# when you do a runtime cast, it would silently, not do anything or not throw an exception or yes. So yes, and I think that's what you're saying too. Is you want to you want to reason about the expected behavior of your program. Sometimes you specify that in your types, Sometimes you specify that with runtime constraints, and both of them should be predictable, and it should be observable.
I'd like to come back perhaps to more centered to the sexy types. So now before we were untyped, and then we moved to simple types or boring types, and there was big disputes 20 years ago whether we should be untyped or have boring types. I think now, perhaps about Eric and a few others, most people agree that simple types are good enough, especially if you have inference or ML-like types. And the question now is rather move whether we want boring types or sexy types. And I think we want both, but what we lack in and what we should search for is ways to mediate between boring types and sexy types. Because if we can't start with sexy types there, it's been said a couple of times, we can't from scratch write all the invariants of a program. We have a structure of data, so we can write simple types, but some of the invariants will come later. So we'd like to be able to type check our programs with simple notion types and refine it later. So I like the idea of refinement types and perhaps ornaments, which might be one way to mediate in this direction. However, also a question there, because once we have richer types, then we can do, so there are things that we had to be dynamic before we had the richer types. Simple types and some tests had to be dynamic. For instance, if we don't have GADTs, we'll have more cases when we'll say assert false or fail. Once we put the refinement types later, we want to, or GADTs, very weak form of refinement, then we want to be able to remove that. So there might be other ways to mediate, and contracts are another track, because contracts say, I want this to be true, I can't be sure, so if you use simple type, the contracts are dynamic, and perhaps later you'll check them, and then you can remove them. Another track I see to mediate would be to find find a line of things that should be types, and if you want to do finer things, then you should use logic formulas on the side that are not within types. But there again, you'd like them to interact, because if you're able to prove something in the logic, then you would like to then be able, so if you prove to say, oh, it's of that type, but I know in fact it's of that subtype, then you'd like to be able to use it in the language. So these are the tracks, and there might be others, and we should explore them more and find good ways to have both at the same time and find the right balance between expressiveness and practicality.
Yeah, so can I add something to your question to you guys, is that should this type system have a clear boundary between compile time and runtime, or is it okay to kind of move some of the type checking that you cannot decide at compile time to runtime, and now the errors might happen later, but they are not flagged by the compiler?
That's okay. It's more complicated, but it's okay. I think it's a good framework to think in. My money. But just adding to Didier's question, I always wonder whether we're a bit fixated on thinking what type does this function have? So a function has one type. I think functions probably have lots of types. So that I know reverse function returns a list whose length is the same as its input, right? And if its input is ascending, then its output is descending. So it has many properties. And if you want one type to express them all, then it becomes a kind of humongous megatype that nobody can understand. It's actually, what you want to do is to specify lots of properties, or maybe ornaments, kind of independently. I don't know any system that does that yet, but I'm pretty sure we're going to want one.
Can I have a microphone? Yeah, so this is sort of key question about the role of types versus logic, where I think flexibility is more important than opinion. There's a tension between whether types should be suits of armor that protect us, they make all the guarantees we might need to get through life, or whether they're just like clean underpants, something that keeps us sort of basically decent and comfortable. as we go about our business, and it's amazing how many kind of how many properties a nice pair of underpants has these days, but you really shouldn't expect everything from them. Yes. So I mean, in terms of, I think the point though is that we do want enough language to explain what we know and what we don't know. So in particular, exactly to model a situation where there's some stuff which is not statically guaranteed, and we want to know that we are doing the runtime test that will give us the authority to proceed. So that's the thing that we need to check statically. We need to check statically that we've coded up the right runtime test. And I think we're stuffed if we can't express that kind of thing as well.
I have a question to Haskell and Agda developers. So the type inference and check-in algorithms for your runtime, so are they implemented in Haskell and Agda, or is it C?
They're implemented in Haskell.
Do you mean what language is the compiler written in?
No. So in which language the type inference and algorithm is implemented?
In GHC is written in Haskell. So
entirely.
The type inference engine is written in Haskell.
Okay, thank you.
Yeah.
And Agda is also implemented in Haskell. We're not quite at the point where we feel comfortable implementing Agda in Agda.
Although it is possible to write down types of well-typed, dependently typed terms, so it won't be long before we have something like Agda in Agda.
But only if you have 2 PhDs.
And a large mental stack.
So actually, a concrete question I'm wondering about. Imagine my type inference algorithm at some point needs to solve linear constraints, yeah? And so I'm wondering, if I'm writing simplex in, say, Haskell or Agda or Camel, so what should be the dependence, these rich types that I'm decorating my simplex algorithm? So should be simplex invariants, or what do you expect there?
Okay, so what's the question you're asking is that if the constraints in your type system fall into a class that we have good solvers for, good decision procedures for, maybe we should just use them, right?
No. My question is, whenever I'm implementing something that is moderately sophisticated like simplex, so actually what information I should put down into types? Beyond like, oh, this list is not empty, or this coefficient is positive. So I don't know. So invariance from simplex from Scriver's book, or?
I don't know either. I mean, I haven't implemented the simplest algorithm recently.
Well, or maybe for unification. I mean, does the type of unification tell you that you will find the most general unifier, for example?
Of course it doesn't usually.
Yes, but it should.
Unless you're willing to invest a significant effort. Yeah. So
which Connor has, is that cool?
Well, so a while ago, so the type of the unification algorithm that I wrote at the time just involved the number of unsolved variables in the problem, and that just adding that information to the type was enough to get rid of the termination proof obligation. So I thought that was a bit of a win. But in terms of more functional correctness, that I did as a proof afterwards, which was sort of greatly assisted by not having to do a termination proof. But over time, more stuff got moved into types. So, for example, these days, the functional correctness of the occur check would be something I would expect to appear in a type using some sort of type level representation of contexts.
It is a universal law that at some point in a conversation about types, the question about what type shall we give the type checker comes up. And at that point, the conversation has become sufficiently incestuous that we should stop. So, I think we should probably wrap up pretty soon, Sam, Mike.
Yeah, maybe I don't plan us to go all the way till 5 o'clock.
Talking about the type of the type checker.
So
Definitely.
before Simon's brain blows up, do we have one more question?
Sort of going in the slightly more academic direction. I these days look at so many papers where the focus is on the type system and its expressiveness and sort of the fanciness of it, if you will, and there is generally so little focus on the ability to do inference, which I find, coming from a whole program analysis background, largely to be, I don't know, disingenuous perhaps. So I don't know, what are your thoughts on that? Sort of balancing inference versus expressiveness.
So the question is, you see too little emphasis on inference?
Yes, way too little.
Yeah, I think it's too hard with fancy types. So we'll have to drop some type inference. So the only thing we can hope is partial type inference. And then I'd like to come back to one thing you mentioned at the beginning, Simon, like in Haskell, should the type system be specified by the typing algorithm that's implemented in GHC, or do you have an a priori specification? So I think, and you also mentioned about robustness, whether types are preserved when you change the program. So I think we'll have to give a full type inference as we have in ML. In the future, we want to keep some form of type inference, because if you don't infer any types, then they're a burden to write. And we have to find, I think we have ways, we know how to do partial type inference now, but we don't know yet how to do it in such a way that it's robust to program transformation, which means predictably. I think they're very close to one another. I found out recently that I think we like ML a lot, and we always emphasize because it has LED polymorphism. But I think something which is more key about the success of ML is that its type inference is very robust. You can do plenty of minor program transformation that will preserve well-typedness. And very few other type systems can do the same. So I think it's really important when in future the inference we'll do, the partial inference we'll keep that properly if we want the language to be successful. Otherwise, you come back to your language a month later, or someone has come to your language that changed a few things and it doesn't type anymore. So then you have to provide more annotations. Where should you put them?
I think we should stop looking at type inference as sort of one monolithic notion. It's got many aspects to it. I mean, as typified by, on the one hand, the let rule, and on the other hand, the variable rule in the ML type system. The let rule guesses what the plan is, and the var rule is the sort of trigger to figure out the details of a plan being applied. And I think guess the plan type inference necessitates the restriction of expressible the expressible plans to those within the imagination of a computer, and that's not a restriction I'm prepared to accept. On the other hand, the fill in the details use of type inference, how is a plan being instantiated locally, that's very doable and extremely valuable, and should be retained at all costs. So I like to see kind of type checking at construction sites and type inference at usage sites.
It's not always clear what is the construction site and what is the user side when you have higher functions.
That's true, but there are sort of good bidirectional disciplines that get you a long way towards that.
They suffer from that. Then you invert two arguments, is typeable in one case and not in the other case. So I think these techniques, they do a lot, and in many cases they do well, but in some cases they just don't do what you want, and they're not robust to just exchanging two arguments, exchanging two, you have a pair and you exchange the components, and it can type check in one case, not the other one.
Yeah, that's unacceptable.
But I agree with the previous things that you said. We'll have to be more explicit about to express what we mean, which is difficult and the program cannot guess, and try to infer all the rest, but thinking about robustness of inference.
So we've been going for 1.5 hours, so maybe we should stop at this point and
always quit while you're ahead.
And thank our panelists for a very interesting session. Thank you.